Alright, so now we're going to introduce resistance and learn the Ohm's law that we typically use whenever we're working with circuits. So a resistor is going to have resistance, and a resistor is a circuit device that has a specific value of resistance. So we're going to learn how to calculate that resistance for a particular circuit element, and that is going to come out of rearranging Ohm's law. So we have Ohm's law here, and we know that current density is current per unit area, so I can sub that in. So since this is on the denominator, I'm going to flip this fraction, so this is why it's area over current. And we also know that the voltage is the integral of E dot dl, and since we're dealing with a uniform field going through a wire, the electric field does not have a dependence on L, so the integral of E dot dl is just going to be E times L, so the length of the wire. So I can rearrange that to solve for the electric field, and I plug in the voltage divided by the length. So rearranging a little bit to solve for the voltage or potential, that is going to leave the current on the other side, traditionally how we do Ohm's law. And everything else left in the formula is going to be our resistance. So resistance is going to equal the resistivity times the length of the wire divided by the cross-sectional area of the wire. So this is why we can build resistors with different resistances. So we're going to use the unit of ohms for resistance, and resistance is going to be represented through that unit by the Greek letter omega. So this is an uppercase omega. So we typically write Ohm's law is voltage is equal to current times resistance. So we expect the voltage and the current for an ohmic material to be proportional, and the proportionality constant to be the resistance. Now, because once again resistivity has a temperature dependence, that means resistance also has a temperature dependence. However, in order to do that, you have to have the resistance in one temperature, and then you can use that to find the resistance at a new temperature. And in fact, we're going to use this property much later in the semester to calculate the temperature of a material that is expanding. We're going to measure how the resistance changes, which is going to give us a temperature back. So we are going to apply this a little bit later on in the semester.